Okay. And so if you go to YouTube, does it say stream? Okay, we're good. All right, welcome everybody. Thanks a lot for coming by and braving the heat. Although it's super cold in here, it's like the two extremes. Can't be anything in between. We got fancy this month and went with Domino's and multiple toppings per pizza. So hopefully you guys enjoy that. Today Josh is going to be talking about big data analysis. This is something where we've received support from the university to do, and that is to build a cluster that's optimized for big data analysis. And so you may be thinking to yourself, well, I'm already doing big data analysis, but just from the current ACCRE environment. What's going on there? So our current environment absolutely supports big data analysis through many of the conventional scientific computing tools that you've grown to know and love, like Python and R and MATLAB. But the issue there is that cluster environment was designed with different sort of base assumptions in mind. So it was designed with high-performance computing, simulation, like molecular modeling in mind, and not big data analysis in mind. And so the tools we're going to begin talking about today come from the Hadoop ecosystem. Has anyone heard of Hadoop? Okay, awesome, about half. And so this was born out of a lot of the big web companies like Google and Yahoo. In the early 2000s, were trying to cope with these millions and millions of web pages and files and such that they were having to constantly manage. And so they developed something called HDFS and MapReduce to kind of help solve those problems. And the interesting thing is it was born in industry and it's only now beginning to sort of work its way into academia. And so Hadoop and Spark, which Josh will talk about today, are huge, huge players in the data science industry in general. So if you're interested in becoming a data scientist, especially going out in the industry, it's very, very likely that your company would be using some subset of these tools that Josh will be talking about today. A few other things. First, we apologize for the brief downtime this morning. That was not planned at all, and we're still digging into it. But things should be available and up. If there is anything odd still going on from your home directory or elsewhere, feel free to open the ticket and let us know. And there was one more thing I wanted to say. We're going to start. So Josh is going to be talking about this new programming environment today called Spark. And you can use Spark from Python. You can use it from R, which will be really convenient, I think, for a lot of users. But if you are interested in porting your code over to Spark and you feel like it's an insurmountable obstacle, feel free to ping Josh and to ping us, and we're happy to sit down with you and look at your current code and to help you convert it to this new environment. And another thing I think we'll probably be setting up is basically Spark and Hadoop office hours. So maybe starting next week, we'll just have a 1 or 2 hour block once a week where you can come by and sit down with Josh, and we can, again, help evaluate your current workflows and see if what you're doing is a good candidate for this new environment. So with that, I will turn it over to Josh.
All right, thank you very much, Will. Thank you all for coming today, enjoying the pizza. This is an intro to using Spark on the big data cluster. And I'm going to ask, first of all, to bear with me a little bit because today's talk might seem a bit more academic and less applied. I'm going to get to some really typical use cases toward the end of the presentation, and I'm going to actually invite you guys to talk and discuss maybe some of the ideas you're having on how to, the kinds of problems you face with big data. But I do want to emphasize the mechanics of what's going on in Spark because I think it's sort of fundamental to understanding why big data works and why this sort of computing approach is useful, but it is also different from traditional HPC. So with that in mind, and because this is very new, I want to be upfront first of all about how to get help with these issues. So Will, of course, has alluded to office hours, but there's the normal channels of submitting help desk ticket. I strongly encourage you to join the ACCRE Forum Slack team, which we do have a big data channel there. We also have a GitHub organization in parallel to the ACCRE GitHub account, which is devoted strictly to big data. So big data-Vandy. We have a blog that's sort of piggybacking off that GitHub site there with some more step-by-step instructions. And then finally, we do take the Big Data Roadshow around campus and meet with research groups if that's something you're interested in. So let's talk about Hadoop. I put this up here intentionally to confuse and wow you with bright colors. Hadoop is the core of big data these days. And essentially, Hadoop is the Hadoop distributed file system, but a huge ecosystem of applications have developed around it. Now, I'm not going to go through all the names, catchy as they may be, or the graphics. But just wanted to give you the idea that it is a very diverse ecosystem. So how is it different from HPC? Well, the fundamental idea in HPC has traditionally been that we have a code running on fairly performant hardware, and we're going to move data to that code. But big data is just the opposite. It's born out of the idea that it can be more efficient to move your code to wherever the data is located, and by taking advantage of that data locality, you can speed up the analysis. So typically what this means in terms of storage is that on our cluster, on the traditional cluster, we use GPFS. On Hadoop, we have HDFS, a distributed file system. So it's not that every piece of data is accessible everywhere in the big data cluster. It's that data resides on different nodes within that cluster. And we'll get a little bit more into the specifics there. There is an emphasis on more performant languages like C, C++, and God forbid Fortran, if anyone's using that. No, I kid, it's a good language. But really the emphasis in big data is sort of being able to program quickly and allowing developers to get to solutions quickly. So you have much more of the niceties in Java, Scala, Python, et cetera. And really this sort of correlates with this idea of imperative programming where traditionally you think about moving through a for loop and I'm going to visit each piece of data once, and when I get to the end of the data, I'm going to do something else. That's imperative programming. In functional programming, the idea is more, okay, I have this idea of data that needs to be transformed in a certain way. I don't really care how I access it, but it's going to be transformed to this, and it's going to be distilled to this. So it's worth reading up on it. It's sort of an interesting new paradigm coming out of programming. So with that in mind, what are candidates for big data workflows that perhaps need to transition from traditional HPC to big data? Well, the obvious first answer is lots of data. If you have lots of data, this is going to work better in general. So typically, data tasks that are embarrassingly parallel, but more or less computationally simple. So it's not so much protein folding would be a poor example of a big data application because we're not really optimizing for, we're not CPU bound. That is to say, the chunk of processing is not coming from the time that it takes to calculate something, but rather the time it takes to move data back and forth, okay? So we're talking about typically I/O-bound applications. And really where this has caught hold in the last decade or so is machine learning, because machine learning in general always gets better with the more data you have, and there have been very clever ways to sort of make machine learning algorithms work within the context of Hadoop. And so this is something we'll talk about towards the end of the lecture today. But also something that you might not think about that actually might be useful to a lot of you is network analysis. So you could think about why this might have come up in the last 15 years or so in the context of industry, social networks, right? There's definitely a need to compute properties of networks quickly and efficiently, and it's become actually very mature, the algorithms to do this kind of thing. And lastly, we won't talk about this too much, but processing data that's coming in a real-time stream. So actually applying machine learning, network analysis, or any of the above to streams of data that you're not actually necessarily storing as is. This is another key component of what Spark can do. So I'm not going to go through this slide in too much detail, but I just did want to sort of point out that the tools for traditional scientific computing versus big data analysis are different and sort of meeting different needs, but that's something you can check out in your own time, I suppose, because I want to get into the meat of the presentation, which is talking about the hardware that we have here available at ACCRE. So, as Will mentioned, we have a test environment set up on recycled hardware now, which has been in use for over a year now, I suppose, which is actually one of the big selling points of big data, is that it can run on commodity hardware, so you're not investing huge amounts of money into the computation itself. Now, what I want to point out here is that the new hardware purchase, so the new cluster that will be coming online this fall, actually has pretty beefy data nodes there. So 80 terabytes of storage, 32 cores, and a half terabyte of RAM. I don't think anyone here probably has a laptop with half a terabyte of RAM in it. So this could be, we're super excited about being able to use these. And I should mention again that this is free for the campus to use. This has been funded, so it's a perfect opportunity to transition to a big data workflow. So I do need to, since we're talking about hardware, I'll just mention that Cloudera Manager is the tool that we use to manage the cluster, and that's probably all you need to know about it. But I did want to show just a snapshot of our ecosystem and sort of the tools that we're managing with Cloudera. So many of the ones you saw in the graphic previously. I'm not going to go through all of these, but I did want to sort of take you to Spark. And in order to do that, I need to talk about these three specific services. So HDFS that we've already sort of talked about. Yarn is the scheduling utility for big data, for our cluster. And Spark is the application development software. So, with that said, what is HDFS? Well, it stands for the Hadoop Distributed File System. It's a distributed file system designed to run on commodity hardware. It's highly fault tolerant because by default, data is replicated 3 times. So if one node fails, you have 2 copies, and your other nodes are aware that a node has failed, so it goes ahead and makes a copy of the other 2 data. It does this all behind the scenes, and as a programmer, it's great, right? You don't have to worry about it at all. So certainly suitable for applications with large data sets. So here's HDFS in a nutshell. You take a big file and you copy it to HDFS, and pieces of those files go everywhere in the cluster. So for different nodes, you'll get different pieces of data, but again, it's replicated 3 times, so chances are you'll have, or you're sort of guaranteed to have redundant copies of the data everywhere. That's pretty much the gist of it. So how do you interact with it? Well, it's not quite like traditional Unix, but it's close. So I'm just going to live demo it here, and probably I'll regret that decision, but let's go for it. So I'm here logged into our cluster, and so the syntax for querying the Hadoop file system is Hadoop FS. But then you can provide commands specifically for that sort of mimic the Unix commands, but they're actually arguments to this Hadoop FS call. So if I do an ls, everyone of course knows it means list the files in the directory. I will list the files in my home directory on the cluster. Yes, from the Hadoop Big Data Cluster. And obviously I'm streaming now, so it's going to be a little slower. But there it is. I've got a lot of stuff in there, right? So it works essentially the same as Unix, but not quite Unix. So I'll give you a hint here. Your home directory, when you log in here, will be /user/your VUNet ID. And when you do that, you'll see the exact same files there. So I'll just for one more demo, I'll show this data drive. This is, again, this is not the same drive as data on GPFS. This is a drive called data that I created on Hadoop, which hosts some specific data sets. So Google Ngrams, for instance, New York City taxi information. So enough of that. This is sort of the command line interface to the Hadoop file system. This Hadoop fs command has a bunch of arguments, 30 or so, I suppose. But here are some of the more common ones. So you can view files, the contents of files, which is very useful. These two commands here are really what the workhorses would be. So if I have data on the normal disk and I want to get it to HDFS, what I'll need to do is use this Hadoop fs -copy from local, which will do just what our graphic here says. It will take a local file, shard it up, distribute it, and you don't have to keep track of it. You can just call that file at any point, and HDFS knows where to go to get that file. So there's some more here. I won't go through them all because I do want to get to the Spark stuff. But here's a really useful one, actually. Question.
Well, I was going to ask, so if I had 10 gigabytes of data on my laptop and I wanted to get it to HDFS, what would the steps be?
So the first thing would be to copy it over to the cluster through SCP or FileZilla, a copy utility. And from there, what you would want to use is the Hadoop fs -copy from local or move from local, depending on whether you want to keep the Unix copy or not.
And then once it's in HDFS, if I want to look at parts of that file, I need to use subsets of this Hadoop fs.
Right,
command. Okay.
precisely. So for example, Hadoop fs-cat user Fido my file will concatenate the contents of that file. And it actually uses globbing expressions too, so wildcards for people familiar. And you can actually pipe the contents of a file into another Unix command like head and just get the first 100 lines or so. Question?
When you copy stuff, is it an actual copy or just any reference to the data?
It's an actual copy, yep.
Are the tools available for like the popular client OSs so you could bypass the copy to the cluster stack? In other words, do a Hadoop?
Like
My
an
laptop.
SCP. Don't believe so at this point.
It's in the plan. We're working on it.
Yes. Working on a solution for that. So, everyone's an expert on Hadoop FS now, so let's move on to Yarn. So Yarn stands for yet another resource negotiator. And its jobs are basically resource management and job scheduling. So we're never actually directly connecting to the data nodes on the cluster. We're operating as clients who submit jobs to Yarn, and Yarn schedules those jobs appropriately. So this should sound eerily familiar because this is effectively the same role that Slurm plays on the traditional cluster, okay? But it's a bit different because one doesn't really have to, well, first of all, you don't have to write a batch job script, a Slurm script, in order to specify a job. It simply works behind the scenes as is. And so resource allocation is essentially transparent to the user. That should come with a big asterisk on it because you can actually tweak these things, but that's a little more advanced than what we want to talk about today. So Yarn is the intermediary between you and the worker nodes. So let's get on to Spark. This is straight from Spark's website documentation. It's a fast general purpose cluster computing system, which means that it supports high-level APIs in Java, Scala, Python, and R, and an optimized engine that supports general execution graphs. Okay, we'll talk a little bit about what general execution graphs mean, but this graph is not a general execution graph. This shows the ancestry of Spark as it is. Okay, so reading left to right, you see that PySpark and Spark R are sort of wrappers for Python to execute Spark code. Okay, so these get interpreted into Spark. Spark itself is written in Scala, so it's essentially a specialized library of Scala. And Scala is itself a specialized library of Java. So the interesting thing about this is that any valid Java code is also valid Scala code, and any valid Java is also valid Spark code. Long story short, you have many ways, 4 different ways to program Spark, which is very, very useful. And again, it sort of plays into this idea that you want to be able to develop solutions quickly, not necessarily spend your time writing really complex code. And so the other thing that really makes Spark general purpose is that it can run in a number of different ways. So if you're interested, we actually have a demo up on the ACCRE GitHub site, which shows how you can set up a Spark cluster on top of GPFS. So this wouldn't be the recommended way to do it. It's more, what's the word, more educational, just to be able to do such a thing. But as we mentioned, it runs on Yarn and it runs on Mesos if anyone's interested. But let's get down to the nitty-gritty of it. So I want to run a Spark job. How do I do it? Well, the first way, and probably the best teaching tool, is to run the Spark REPL. So REPL is a read, evaluate, print loop tool. It's essentially a shell that runs Spark code for you. So the general way to call this is to point to your installation of Spark and then the command Spark shell. So on our cluster, we actually have 2 different versions of Spark going. And I want to emphasize here that since most everyone is picking this up as a new tool, stick with Spark 2. It's got some optimizations and some more functionality built into it. So I'll just mention here that one can start a Spark shell with Spark 2 shell or PySpark 2. So this gives you the option of interacting with the entire cluster via a Scala Spark interface or through a Python Spark interface. And this is what we'll use for the rest of the presentation. But there's also a more general way to submit jobs or jobs that you've really fleshed out what the code is supposed to do, and that's through Spark Submit. So Spark Submit, or rather Spark 2 Submit, will accept as argument either a jar file, so compiled Java or Scala code, or a Python script, okay? So super useful. And you'll see, if you read the documentation for Spark Submit, you'll see that there's many different ways to configure it. But in general, if you run Spark Submit or Spark 2 shell on our cluster, you're already configured to use Yarn, which means you're going to use as many cores as you're allowed to, which is really great. So now that we know how to use, to invoke Spark, let's talk about a simple application. So word count in Spark. Word count is the hello world application for Hadoop and MapReduce, Spark, everything. But the idea is simple. You're going to count the occurrences of all the words in a text file. And for this, we're actually going to use the Scala REPL. So if you're interested, this content basically comes straight from the Spark Quick Start Guide, which is here. And I do want to mention that for this demo, I'm going to be using Scala Spark. And you're probably thinking, well, man, I already know a little bit of Python, or I know a lot of Python. Why is this guy trying to teach me Scala? There's some very good reasons to do this. It's becoming sort of the lingua franca, as they say, of data science. But also there's some really nice type checking built into it. So I think you're going to be pleasantly surprised that it's pretty easy to understand. It's very much like Python in some ways. But having said all that, if you look through the documentation for Spark, you'll see that you have example code in both Scala and Python essentially everywhere you go. So you're able to switch back and forth between the two. And it's quite simple to pick up on. So I think you'll be able to follow along. Don't yell at me too much, please. So the first thing we're going to do is read in a text file using the Spark context. So the Spark context, traditionally or conventionally written SC, is the entry point for the Spark API. So it's already created for us in the REPL, so why don't I switch here and just demo this in the REPL. So all I've done here is call Spark2 shell, okay? So I'm in the shell. What I want to do is create a new value. It's called lines RDD, and it's equal to sc.text file. Okay, so amazing, right? We see that we've created this value called lines RDD, which the REPL is telling us exactly what it is. So lines RDD is this class, an RDD of string that's coming from this file, okay? So you're probably thinking at this point, what in the world is an RDD?
Where does that file live? Is that an HDFS or is it?
It could be on HDFS, it could be, and in fact is on my home directory on the cluster. So it's a normal file. We'll talk a little bit about the mechanics of that in just a minute. So resilient distributed data set. Everyone say it with me, resilient distributed data set. This is the core idea of Spark, and that's that an RDD is a fault-tolerant collection of elements that can be operated on in parallel. So resilient, why is that important? Well, if we're talking about hundreds of gigabytes, terabytes of data, and we're operating on them, we're going to need a few nodes to be able to do that, right? And if one node fails, we don't want to restart the whole process. So the idea of resilient is that parts of this this data set can crash or whatever, we don't care, we can recover from that. And that's baked into the programming of the RDD itself. So the other thing is that the parallelism on this RDD actually happens magically and transparently to you, which is, if you think about it, a very big departure from traditional HPC. You have to either specify through job arrays or specify MPI calls to different nodes, things like that. Here in Spark world, we know that we're going to be operating in parallel, so we have RDDs to do all of this hard work for us, and we can just let it do its thing. So resilient distributed data set. If you don't take away anything else, that's what you should remember from this one. As such, because an RDD is distributed, we can't actually view it directly. So to view an RDD, we have to send all the data to a single node, okay? So going back to Will's point here, where did this file live? This spark readme.txt happened to be in my home directory. So I'm pointing relative to my home directory, that file. What Spark does when I created this text file, though, is to send pieces of that file to different nodes in the cluster, okay? So it partitions it according to how it wants to partition it and sends it there. So as such, I can't just read it. I have to grab it back. I can do that with this call here, lines RDD .collect, okay? So collect is going to send all this data back to a single node, and then I'm going to run this function for each. So for each element in this RDD, I'm going to print the line, okay? So what we'll see is this does take a second, but because it's been distributed, so it has to go and actually fetch it from different partitions. So here we've just printed all the output, and it's pretty big, but this is the README for Apache Spark, okay? So that's just our dummy file we're playing with. We can see that this RDD happens to be an RDD of string, so each element is its own string. And you'll notice too that it stayed in order in this case. It reads as it should. So here, the same duplicated content on the screen. So that's great. We have an RDD there. What can we do with this thing? Well, many of you have probably heard of MapReduce, so we're gonna delve into the world of MapReduce here. And mapping simply means that I'm going to transform these elements in this RDD into something else, okay? So usually our data is not exactly the way it needs to be, or it doesn't give us information as is, so we need to transform it. That's the entire idea behind mapping. And so mapping actually is a common function in Python. It's common in Scala as well. So here, if I just have a Scala string called foo, it's just a simple line of text. I can actually map this string into an array of strings using this special .split function. And those of you who know Python know that this works exactly the same in Python. So when I do this, when I call split on a string, the result is an array of string. So essentially what we want to do is do this to every element of our RDD, okay? So let's just do that. If we want to know the words per line, what we can do is apply this function here, the splitting function, to each line in the RDD. Okay, so let's take a second and let that sink in. So we started with this lines RDD that's an RDD of string, and we're going to map each string with this anonymous function here, which takes a string and splits it. Okay, so those of you familiar with Python will know that the anonymous functions in Python, you use lambda x, right? Or it's a lambda function. The same idea here. We're just constructing this function that tells us how to map it, okay? So the result here that we call words is an RDD, which is an array of strings, okay? And if we want to know how many words are in each line, then what we need to do is just take the size of that RDD. So I have this words RDD here, and I'm just going to map it. I know that each element is an array of string, so I'm going to take the array of string and apply the method size, which will give me the total number of elements. So if I do this, then I can store the result as words per line, and I'm just going to print out the first 5 elements of this RDD. Okay? So let's go back for a second and look at what our original data was. It was hashtag Apache Spark, and then a space, and then Spark is a blah, blah, blah. So what, about 13 lines, or 13 words in this line or so? So that's exactly the result that we have here. The first line, which was just Apache Spark, then a blank line, which counts as 1 in this case, and then 14 words, etc. So, questions? What doesn't make sense at this point? Or what does make sense?
The mapping function, like in practice, if I had a large data set, the mapping function is what would allow me to control how that data gets split up and distributed across my cluster. Is that right?
The mapping is transforming each element of the RDD independently. So you could think of this as a completely independent transformation of whatever the element is in your RDD. Okay, so here we've mapped a string of words into an array of words, and then we've mapped that array into its size, so an integer. So we started with a string, went to an array of string, and then to integer. So that's exactly words per line is an RDD now of integers.
So it allows you to sort of reorganize and restructure your data to make it easier to analyze and process.
Precisely. Yep.
And every time is a new RDD because they are immutable.
Yes, that's a very good point. So I'll get back to that in a second.
So because of the distributed nature of the RDD, I mean, do you want everything to be an RDD? Like you said, that with the text file, like it takes a little while to just show a text file, which would be instantaneous on like my laptop. So
Sure.
do you need to have 2 different directories where one node somewhere where you're storing regular data that's not RDD, that's maybe smaller files, and another one that's RDD? Because it sounds like there's some overhead with all the distributing. And if I've got a small data set that I'm using along the way, I don't want to deal with that overhead. Is that right? Or is that?
Sure. So here's a good example that's actually a real one. Say that I'm parsing through 500 gigabytes of website data, okay? And there's text and content from blogs. These are food bloggers. And I have a dictionary of food words that tells me what the flavor profile is for a given word. So if I see bacon in the dictionary, it's going to be delicious or terrible or whatever. The dictionary itself is not going to be a huge file, right? It's going to be maybe a few megabytes. So in that case, you can certainly store that locally, read that in through Python or Scala as a normal text file, and use that dictionary as is, as a non-distributed data set. There is a mechanism to broadcast that data set to every node in the cluster, okay? So you get a copy of that thing everywhere, and that way every node can look at that and reference that read-only data, if you will. So yes, you're right. In that case, you wouldn't want that. For our example, it's purely educational here. So yeah, for a text file of a few kilobytes, no, this would not make sense to do that. But in terms of all the half a terabyte of website data that you wanted to analyze, certainly you want that to be an RDD. So good question. And as Davide mentioned here, this is sort of a key point that is maybe not truly necessary to get it to work, but is necessary to understand. And that's that each time you transform an RDD, you're actually creating a new RDD. You're not mutating the RDD that's there in place. And the reason for this has everything to do with resiliency, okay? Because I can't know for sure when I'm going to access a piece of data, or that is to say, the nodes themselves don't know exactly when they're going to access a piece of data, and they're all doing this in parallel. So if they were all trying to modify the same piece of data, they would get into race conditions, and it would be very difficult to guarantee that you were going to get a consistent result every time you ran your program. So the idea is that these structures, okay, so it is an important point. Maybe not necessarily critical to get it to work, but good question. So that was the mapping phase. So if we want to get just the total number of words in this document that we have, we can sum up our words per line RDD. So remember, it's an RDD of ints. And we're going to apply a function here, or a method, which is .reduce, okay? This should sound familiar, map reduce. So it also takes a function as its argument here, which is a lambda function. So it takes two elements, and I haven't told you what those are, but it tells me how to combine those two elements together, okay? So we just said mapping is transforming the data. Reducing is combining data, okay? And that's the entire MapReduce paradigm in a nutshell. So this would be useful if you want to compute the mean of a data set or the standard deviation or something like that. You have to have a way to combine values together. And that's exactly what this reduce mechanism is doing. So if we look at this function, it takes two parameters, A and B, and I'm just going to give you a hint here. These are both integers. And it's not saying, the normal way you would calculate this sum in, say, C would be, okay, let's create a for loop, and for I is equal to 0 to n, let's step through each element of it. And we're going to keep a variable called total, and we'll just add to total every time. Here the model is different. Here's what we're saying is that if we had a set that was only two members, that only contained two members, how would we combine them? Okay, we'll just add them together. But it doesn't actually matter the order in which we combine the two. And that's, again, harkens back to this whole idea of parallelism, in that you can't really know the order in which your operations are going to happen necessarily. So luckily for us, A plus B is equal to B plus A. And so there's no, this is a commutative operation, and it's perfectly valid as a reduce step, okay? So you could think of others that might not be. So trying to directly calculate a mean, you don't know what the denominator is a priori, so you have to calculate means in 2 steps. So I might be getting a little bit into the weeds here. But again, let's take a look here. So we started with an RDD of int. We applied our reduce method on it, and our result is this value total, which is an integer. Okay, so that's another hallmark of this reduce step, that we take this distributed thing and we collapse it down back into our normal Scala objects. Okay, and so you see this thing isn't distributed now anymore. It's an integer that lives on the master node, as it were. And so it's directly viewable. All right, so this is sort of a rehash of just what I said here. But it is critical that you understand that the order in which you do this reduce operation cannot matter, okay? That's maybe admittedly a tough way to think about things at first, but that's why we're doing the Hello World example, so you all will understand the mechanics of it, no problem. So here, let's just recap. The map reduce paradigm is that you have some data, it's distributed typically, and you transform it in some way. So here I've just put some examples of some transformations. So we saw map, but certainly you could apply a filter function. So we want to get rid of lines that say the word Spark in them. We can totally do that with a filtering function on our RDD. We'll talk about flat map in a minute. But other things sort of SQL-esque, or if you know, if you're familiar with databases or set theory, then join, union, intersection. These are all things you can do to map your data. And then reduce, so the common ones like reduce, what we saw, count, which is simply count the number of samples. Maybe sample is one where you just generate a random sample of the data. So in a nutshell, that's it. There's certainly nuances to these functions, and there's actually many more functions that Spark exposes to us for doing this kind of analysis. So let's take it a little bit further. All we did there was count the total number of words, but now let's say that we want to create a list of the most common words in this document. Well, that truly is what word count is. But let's think about, just in pseudocode, how we would do such a thing. So the first step would be to map each line into an array of words. So we're just going to split it so that we're not looking at sentences but words. So you've seen that already. The second step is that we're going to match each a word into a word value pair, or tuple. So who here can tell me what a tuple is? Who doesn't want to tell me but knows? You. Is that a hand? No. Okay.
It's like a row of ordered list of different types of data.
Sure. Okay. So it can be ordered, can be different types, can be the same type.
I thought, well, it's like a list, but it can't be changed.
Yes, it is immutable. That's very good. So it's really a generalization of a double, a triple, quadruple. A tuple is this immutable list-like thing of a certain size, so of size n, would say. So this happens to be a tuple of size 2, and generally in Python and in Scala, you denote tuples with parentheses, okay? So this is a tuple of string and integer here. Okay, so that's exactly what we're going to do to our text file, the words that we're pulling out of our text file. Okay, so in this tuple, the first element is the key, which is a unique identifier to this tuple. So let me ask you this. Could an integer be the key of a tuple? Or could it serve as a key into a word, just abstractly. It doesn't matter what language, but we see here that a string would be. How about an integer? I'm seeing some yeses. What about a float? Are there a discrete number of floats? Well, yeah, but they can't. So essentially, a key has to be uniquely identifiable. It has to be hashable. That is to say, that if you run a certain function on it, it's going to give you the same output every time. So yeah, that's a little bit farther than I need to go there. So the first element is a key, the second element is a value or payload. And this idea of key-value pairs are sort of special ideas in RDDs, okay? So they actually have a name for them, pair RDDs. And the reason is that sometimes we want to group data together, okay? And so the key is the thing by which we're going to group our data, okay? So if we wanted to calculate all the occurrences of the word the in our corpus, then for every time we see the word the or the, we would emit a key and the value 1 for this every time we see it, okay? And we can group all those occurrences of the by the key the and sum them together. And that gives us the total occurrences of the word in the corpus, okay? So I'll take a second and maybe say that again. So key value pairs are the mechanism for allowing group by operations. And if you think about it, this is the way it kind of has to work, okay? So we're going to use a special function called reduce by key to do this for us on this particular RDD, okay? So I know I've thrown a lot at you here, and this is pretty messy code. I probably wouldn't recommend doing it this way anyways, but I just want to show you that these commands can be piped, and once you understand the flow of data through it, it sort of makes sense to you, okay? So let's start back at lines RDD, which is an RDD of type string, right? We're going to apply this mapping function flatMap to it, and we'll get to what that is in just a minute. But we know that this thing has to take a string because it's a string element in lines RDD. So for this string, we're going to split it on spaces again, okay? When we do that, the result will be an array of string, right? Well, for each element in this array, we're going to map the word to its tuple key value pair, which is word and the integer 1. So what is the significance of putting a 1 here? Why not 10 or 20?
Because that's the same word. It has a common one.
Single word, yes. It's occurred one time. Every time I see it, I know that it's occurred one time. So each mapping function is just working very locally. It says, okay, I know that I see this word and it's here once, so I'm going to emit that value, and I'll let some other function take care of summing those together. I'm not keeping track of the total number of words as I go along. I'm just passing on the information that I have, okay? So what we have here, the results of this expression that I'm going to highlight here would be an array of tuples, okay? FlatMap is a special function that says, okay, I know you're going to give me an array when you perform this function here, but I don't care. I don't want that array. Just flatten it out. Just for every element in that array, create a new RDD element, okay? So it's sort of like exploding. I mean, you see this happen in other contexts too, computer science. But it's one that kind of comes up quite a bit. And so in this context, what we're doing is just creating that RDD and then flattening the whole thing out so that now the RDD that we're looking at up to this point would be an RDD of tuples, right? Does that make sense to everyone? Questions?
Are they summed yet?
They're not summed yet. Good question. So we have an RDD there. So the last step of the pipeline here, and it's actually chained with this dot here, is to reduce by key. Okay? So this is essentially the same reduce function we were using before, but now what we're saying is that we're going to reduce by key, which means we're going to group all the like keys together. So the key is just the first element of that tuple, so it's whatever word is. So that guarantees that all the thes and all the Sparks and all the Apaches that occur in that document are going to be grouped together, and we can sum them up together. Okay? Question?
How would word frequencies be different if you had used map instead of flat map?
You need another step to map your array to
So if you
to expand it.
map, what would word frequencies be like? What would be the structure? Would it be an array of arrays or?
It would be an RDD of arrays of tuples. Okay? Yes?
So if we have a word, say Spark, and the S is capitalized, but then we also have Spark and S is not capitalized, would this count as the same?
That's a good question. In this case, it would be different because the only transformation of data we've done is to split on white space, okay? So it's just, and actually you split on single spaces. So yes, our mapping function, this mapping here, we could make that a more refined function to say, let's capitalize everything, or let's lowercase it, or let's take the root of the word, but not the ending. So, good question. Others? Wrap it up, yeah, okay. So, here's the nice, the graph, the directed acyclic graph, the generalized execution graph that we talked about earlier. So this is actually what's going on under the hood of MapReduce. I encourage you to take a look at this. We'll have this posted on our website. Just wanted to give you an idea of the kind of things you could do. So this gets much more complex, but I think you guys will have a firm understanding now of the mechanics, and the mechanics don't really change depending on the API. But you can read CSV files for sure, and you can query them using SQL-like syntax. So I just wanted to show you a little bit. There's a whole machine learning library that Spark maintains and has developed, which is extremely useful. So it has things like logistic regression, clustering, random forests. I'll show you here. I have an example on YouTube of how to classify SEM images. So SEM and X-ray data, some of you may have for sure. What you can do is actually use these built-in sort of classifiers, which you don't have to program yourself, and create pipelines of data to do things like that. You can do computation on taxicab data, for instance. So here we've calculated the most popular taxi pickup / drop-off area in New York. And we did that using the PageRank algorithm, which comes baked into Spark and is what Google has used for years to compute, to direct to your web searches, to web pages. So this is really, I mean, cutting edge from an algorithmic standpoint. So I'll just try to finish it up, 5 minutes over here. So my tips: read the documentation for sure. Use the check the GitHub repositories for example code. And the biggest one, I think, or one of the main ones, would be use a good integrated development environment, which will prevent a lot of your mistakes before they happen. So again, apologize for going over here, but we're here to help you. I am here to get you up and running. Don't hesitate to contact us through any of the channels, and we'll be happy to consult with you. So thank you very much.